Hello, welcome back to GEO 572 Advanced Hydrogeology. Today we're going to be talking about different reaction types and types of reactions we might see in the subsurface, and then how we couple that into reactive transport simulations. So let's start thinking about types of reactions we might have in the subsurface. And let's do that by just, considering a regional flow system. We got a mountain, a long flow path, and then we got a stream down here. So here's our stream, and we got a water table in here that comes down here and meets the stream. And groundwater in general is being, recharged near the top of the mountain and flowing towards the stream. Okay, and there's a variety of different kinds of reactions we can have as in this sort of setting. And the first we might think of is that, we start out and water percolates here in the recharge zone down through the mountain. It's fallen as rain. In here, we're in the vadose zone and there's oxygen in our water. And then we hit the water table, the water descends and moves. And as we do that, oxygen gets used up, all right? And oxygen turns out to drive all kinds of reactions. And in this zone up here, we can think about the interaction of this oxygen-rich water with the rock and organic matter and any other species in this zone. And we can get a whole bunch of what we call isothermal reaction fronts. So and in these fronts, essentially, we've got, we start off and we've got this oxygen-rich water, coming in, O2-rich water coming into our zone, and it starts reacting with the native rock. So we'll call this zone 1. And here we've got highly altered rock, zone 1, altered rock from oxic water, so we'll call this oxidation. All right, we oxidize all kinds of stuff in here, and as we do that, we use up O2. So our O2 concentration in our water goes down. All right, and we in this zone here, we dissolve the most easily dissolvable minerals. So let's just say not easily. We're dissolving mineral, whatever, mineral 1. And then as we progress down, we go to zone 2. All right, and here we have less oxygen, but now we are dissolving mineral 2. All right, and then this zone here is zone 3. And here we're dissolving, say, mineral 3. All right. And as we do this, O2 continues to go down until out here we get to unaltered rock, because we've used up all our oxygen and we're no longer dissolving. All right. And these zones get called reaction fronts. All right. And they basically form as water interacts with the rock and loses things like oxygen, changes the different, like as an example, mineral 3 here is probably the most soluble mineral. And here we're in our first zone, we've already dissolved all of mineral 3 because water's been moving through here the longest with most oxygen. We've already dissolved all of mineral 3 out of zone 2, but mineral 3 is still left in zone 3. Mineral 2 is the second most soluble, and we've already dissolved that out of zone 1, but there's still some left in zone 2, and it's still there in zone 3. And in zone 1, all that's left is mineral 1. All right, so these zones are called reaction fronts, and they're largely get driven by the presence of oxygen and how we use oxygen up. We might also have a groundwater flow path that just enters a new geology, all right, and there's some soluble mineral there, and we use that up along the flow path. But these isothermal fronts form along a flow path. And they form due to preferential solubility of different minerals. So an example of this is, when we're looking for recharge zones and areas where the groundwater table is active and fluctuating when we're drilling, say up in the mountain blocks, one of our key indicators is the presence or absence of oxidized iron. Iron is pretty soluble, but if it's in its oxic form, we know there's oxygen. So we know there's oxygen-rich water making it into the system. All right. As we go deeper into the system, where the oxygen's all used up, we won't have iron staining. The reduced iron is more soluble and doesn't precipitate out, and we won't see any kind of iron staining. Okay, so so these are just zones where water along a flow path, we get different zones of reactions. We call those isothermal reaction zones. Another type of reaction would be mixing zone reactions. So, so here, where the water is discharging into our stream. So here we have surface water. Right? And it's really rich in oxygen. And here we've got groundwater that's taken a long flow path, and it's very poor in oxygen. All right. And this zone where the surface water and the groundwater mix is a mixing zone of two waters of very different chemistries. And because of that kind of mixing, we can drive all kinds of different reactions. So we have, so we can think about these kinds, these areas of reaction as two different end members. One is happening along a flow path, water rock interaction along that flow path are sort of driving changes in the fluid chemistry. And this is sort of a long flow path isothermal reaction. And then the other one is where we bring water that's had time to come to equilibrium, say with a rock in a different environment, and we mix it with water of another type. And that zone there where those two waters of different chemistries interact becomes a mixing reaction. All right, and we have different chemistries of those waters that drive different reactions. So these are the two sort of, I'd say, end members of types of reactions that we might see. Sorry, not types of reaction, zones of reaction. So what I want to do now is sort of break out a general chart of reaction types. That we might see in these two different kinds of zones. So these are all some subset. This is going to be like a flow diagram of chemical reactions. And these chemical reactions within our advection dispersion equation, I'm going to write it shorthand. So our dispersive term, our advective term, plus R. These are our chemical reactions, and these are sources and sinks in our advection dispersion. So all of these reactions fall under this chemical reaction term. And we had an example of a first example of these kinds of reactions with absorption. All right, and we talked about how sticking to the surface might be a source or a sink of solute from the aqueous phase. All right, so all of these chemical reactions can be put under this reaction term in our advection dispersion equation. And we can break them out into two main branches of reactions. And one set of reactions are fast and reversible. And the other set is slow and irreversible. All right, so two main branches, fast and reversible, and slow and irreversible. And then we're going to break these two up into two main classes, homogeneous and heterogeneous. All right, and let's define this really quick. So a homogeneous reaction, we'll write down the definition in a sec, but a homogeneous reaction in general is one in which the phases are all the same, all right? So as an example, a reaction where all the reactants and all the products are in the aqueous phase or dissolved in water would be a homogeneous reaction. A reaction where where we say dissolve a mineral or precipitate a mineral, some of the reactants are in the solid phase, some of them are in the aqueous phase. That's a heterogeneous reaction. All right, so homogeneity and heterogeneity, when put towards chemical reactions, essentially mean the homogeneity or heterogeneity of the phase of the reactant. All right. So homogeneous, fast, and reversible reactions we're going to classify as type 1. And we're going to put this arrow down here, and we'll talk about type 1. But type 1 reactions are essentially everything that most of what you've worked with in chemistry, all right? These are classic reactions, and if they're fast and reversible, that means they're equilibrium reactions. They can go either way, and essentially the reaction, all reactions in reality are what we'll get to these later, are called kinetic reactions, but these ones happen so fast we can treat them as instantaneous. All right, heterogeneous, fast, and reversible. Well, we've already talked about one of these, and it's a class of reactions that we're going to call surface reactions. All right, and so this is reactions between stuff in the aqueous phase and the mineral surface. All right, so the first one that we're going to call this a type 2 reaction. And an example here would be linear absorption. This is a fast equilibrium reaction that includes interactions between the aqueous phase and the mineral surface. This one we're going to call classical. This is interactions between mineral phases and aqueous phase. And essentially, this one ends up being dissolution or precipitation, just sort of typical ways we think about heterogeneous or reactions between solids and liquids. And a lot of times we think about them dissolving or them precipitating. All right, slow and irreversible. We can have this be a homogeneous reaction. And these are essentially kinetic aqueous reactions, all right? So they're all in one phase, but because they happen slow, we need to think about the rate at which they happen. They don't happen instantaneously. And so there'll be kinetic reactions, and we'll talk about some examples of those in a second. And we're going to consider in our sort of most of our reactions, we'll consider these kinds of reactions. Well, we will consider analytical solution with these kinds of reactions. Heterogeneous and slow, again, we have surface reactions. All right, and these would just be like kinetically limited absorption. All right, these are absorption that is happening, but it happens slow enough that we need to think about the rate at which it happens. And then we have classical again in the heterogeneous oh, all of these fall under heterogeneous. So I need to do some erasing here because our flow diagram is messed up. All right, heterogeneous. And these can be surface reactions or classical precipitation dissolution reactions. But they're just happening slow, all right? And we need to think about the kinetics. Sorry, this would be VI, and this would be VII. All right, so this is our general classification. Basically, is it fast or is it kinetic? Is it homogeneous? Is everything happening in the aqueous phase, or is there interactions between phases? All right, and commonly we think about aqueous and solid, but this could be solid or liquid and gas. It could be solid and gas. There's all kinds of phases for us to interact with here. And heterogeneous interactions must include the fact that there's more than one phase. So let's go through and give some examples, at least of the most common ones and ones that are commonly talked about or used, and in particular ones that we'll be wanting to use for our simulations. So fast reactions we'll start with first. And let's go homogeneous. So this is type 1, fast homogeneous. And these are the classical reactions that you're used to seeing. So these are essentially instantaneous sources or sinks of solute. Let's say of a species, because what happens here is we might lose product in one form, but because of mass conservation, we're going to still have atoms in the same form. So it depends on a little bit on what we're tracking. But the basic idea here is that here we have a chemical reaction of 4 generic species, all right, A, B, C, and D, and their stoichiometry is little a, little b, little c, and little d. All right, and if it's fast and irreversible, we can write an equilibrium constant, fast and reversible, that looks like this. KEQ is big C to the little c, big D to the little d, big A to the little a, big B to the little b, all right? And this is sort of the classic equilibrium equation that we're used to seeing from chemistry 1. And this equilibrium constant is something we can measure, and it tells us if we have these 4 species together, that these are the concentrations that we would end up with, all right? Generically, you know, this is for a 2-member reaction. In our reactions can get very complicated in geochemistry, so we can write this generically as the product I equals 1 to the number of products, all right, of stoichiometry P to the VP of species. We'll call this P, sorry, not I. P equals 1 to P equals NP. Keep writing G instead of Q. All right, and all this guy is just like a sum. It just means that it's the product of all of these things. And here we'll do reactants. Where M here is the concentration, I can put brackets on here, of the product P, concentration of the product or the reactant R, and V sub R and V sub P are the stoichiometries of each of them, right? So all this is a way to shorten this notation in case we have lots of these guys. Another thing that I talked about a little earlier, so for each reaction, we have a K equilibrium equation. All right, so each reaction that we consider, we have this equation. So this would be one of our mass balance equations. And then we have another one, and that is that, you know, for any species, we're just going to say big M. All right. The total mass of that species is the elemental concentration. So this would be like, let's say this is oxygen. There's some amount of oxygen just dissolved in the water, right? Plus all the places where all the different species where oxygen is present. And this is the stoichiometry. So, you know, oxygen might be, for example, in the hydroxyl ion. It might also be in CO2. And so if we were interested in like tracking the total oxygen content, we would need to think about that dissolved in water and that is put into all the different other complexes. So we have two constraints, and that is that we can think about all these different equilibrium reactions, and then we can also say that mass is conserved. So all the oxygen throughout all these reactions has to remain constant. And so what we do when we do reactive transport is that we will say transport a bunch of species. We'll look at all their concentrations at the next step, all right? If they mixed and concentration ions are out of equilibrium, we have to re-equilibrate everything according to the equilibrium constraints and according to the mass conservation constraints. We have series of equations that we solve simultaneously, and then we re-equilibrate everything. And we think about that as like we transport it a ways, we see if things have mixed. If they have, we instantaneously react those guys. All right. So this, I would say, is sort of one of the classical forms of reactive transport, and that is that we consider groundwater flow, and we track species for a bit of transport, and then we check and make sure that equilibrium is achieved between all the species that we are tracking. And so the big things that we end up doing are deciding which species we are tracking, which reactions. So what equilibrium reactions are we going to track? What species, M here, are we going to track? And then we solve a series of equations that are the equilibrium equations and then the mass conservation equation. And we do this for every species that we're going to track, all right? You can imagine that the more and more reactions that I need to consider, the more and more species I need to track, the harder the bookkeeping gets, and the more complicated solving these sets of equations for every one of these species becomes. We're not going to do a ton of this, but this is, really common in the reactive transport, and I want you guys to be introduced to it at least. So fast surface reactions, type 2, all right? Well, the classic example here is the linear absorption that we have talked about already, all right? And remember, linear absorption said that, the concentration on the surface, or the sorbed concentration, was equal to some constant, Kd, the equilibrium constant between the aqueous phase concentration and the amount sorbed onto the sediments. All right, and we talked all about this, so recall that this led to the retardation factor in our transport, all right? And we talked about what Kd is and how the units of Kd and Ksorb work out, or C aqueous and C sorb work out. So this would be sort of our first and most common example of fast surface reactions, and the one that we're going to consider in this class. But there are many others. So another example is Langmuir absorption. And what Langmuir absorption says is there's a finite number of absorption sites on a mineral. So let's think about what linear absorption says. It doesn't matter how high this aqueous concentration is, we're always going to be able to, our C absorption will just continue to increase forever. All right, and it's just going to be a straight line. And what Langmuir absorption says is, well, there's some finite sink. At some point, you've saturated all your mineral surface with this sorbed material. And so it basically starts with this. It says the concentration in the water over the concentration on the sediment is 1 over alpha beta plus the concentration over beta. And alpha and beta are fitting constants. All right. But essentially, this flattens out the concentration, and we can solve now for C sed. Let's just do this. Alpha beta times C over 1 plus alpha C. And what we see is that, the higher and higher the concentration gets, then there's some limit, because our denominator is going to keep getting bigger and bigger and bigger as this gets higher and higher in concentration. Another example of these kind of reactions is what we call ion exchange. And here we're going to think about this reaction as a sort of classical reaction, but it's a heterogeneous equilibrium reaction. So an ion exchange, we might write it like this, QA, for example, minerals such as clay. So this represents the complex of A hooked to clay, all right? And Q is the stoichiometry of that, plus P, B, Q plus is the ionic charge of B, all right? This goes to P, B, clay, plus Q, A, P plus. All right, and and what this reaction signifies is B, whatever B is, taking the place of A on a clay, all right, and releasing Q. And so we can write the equilibrium constant KAB is the reactants, which would be X of B, or PE, sorry, B clay to the P, right, times A P plus to the Q over reactants A clay to the Q over B Q plus to the P. All right, so that's ion exchange. So these are all surface reactions that that are fast and reversible. Type 2 reactions. All right, and the most common of which, linear absorption, is the one that we're going to think about in our model. All right, so next we have heterogeneous reactions, fast heterogeneous reaction, all right, so these are type 3 fast reversible heterogeneous reactions. And this is essentially like we've got some mineral and it dissolves into A sub A plus B sub B. all right? And we have a mineral solubility, K min, which is equal to A to the A plus, or sorry, times B to the B, all right? And we can do this shorthand as P equals 1 to NP. I'm going to get rid of something here. There's an activity coefficient in here. If you haven't taken geochemistry activities, brutal concept. So we're just going to say these have an activity of 1. All right, which is what we implied here. So this is the shorthand version. It just says multiply all the products to their stoichiometry. Okay. We don't include the mineral because there's no way to include concentrate from mineral in this equation. Because it's heterogeneous, right? So it doesn't make sense to have a mineral concentration in there. All right, so this is heterogeneous reaction, and this is a really common reaction. And one thing we often do is look at, compare the concentration of, say, A and B to the mineral solubility. And we call that, so you can see whether, say, calcite is supersaturated or undersaturated, and you can decide whether calcite would dissolve into your water or precipitate from your water, or whether it's in equilibrium. So these mineral solubilities and the water chemistry tell us what kind of reactions we can expect with the rock. All right, so slow reactions means we have to include the rate of reaction. They don't happen so fast that we consider them instantaneous. And so these are kinetic reactions. And so we can think about kinetic reactions. So a homogeneous kinetic reaction, the rate might be given like this. Oh, let me write the reaction first. Let me do that. So let's consider a homogeneous reaction. A sub A plus B sub B goes to C sub C, right? And the reaction of A is given by dA dt, right? And that is K1 A to the P B to the Q. We've got another rate here, R sub B, D, B, dt is equal to K2, A to the P, B to the Q. and RC is equal to dC dt K3 C to the R. And so RA, B, and C, these are the rate of production or disappearance of solute. All right. K, 1, 2, and 3. This is the reaction rate constant. All right. And P, Q, and R are the reaction order. All right, and we're going to talk about what that means, but it's essentially the exponent that that multiplies the concentration. So as an example, let's consider a zero order reaction. All right. Then the rate of disappearance or production of A, for example, dA dt, all right, would be K1, and then we would have A to the 0, that is equal to 1, so this is just equal to K1, all right? So what a zero order reaction means, a zero order kinetic reaction means a constant production rate or decay rate, irregardless of the concentration, all right? So one example that I can give you of a zero order reaction that I use is the fact that so helium is produced by the decay of uranium and thorium. The production rate of helium depends upon the concentration of uranium and thorium in the sediments. We can basically consider those constant for the time being until we're 400 billion years later. But so it's a constant production rate, and it doesn't matter how much helium's there, it's constantly being produced by the decay. So that's a zero order reaction, a constant rate of production. A first order is a really common reaction, and one that we'll use and one that people use all the time. And what it says is that the rate of, say, production or decay of a solute is equal to K1 times the concentration. All right, so this is the equation for radioactive decay. All right, for sure, but all kinds of processes get modeled by this. So for example, a really common way to model biological use of some solute would be with a first order decay. And essentially the equation says that the rate of production or the rate of decay of your solute A is linearly proportional to the concentration, at that time. And this ends up giving you exponential decay, all right? Okay, so you can do the same. You can write a lot of these surface reactions that we wrote already in this kinetic form. I don't want to get into that because we're not going to use it, but essentially all reactions can be written in a kinetic form. Okay, so when we do reactive transport, the idea is figuring out how do we couple these reaction equations in with our transport equation. So in the case of, for example, linear absorption, and we'll do it with first order decay, it's pretty easy to write those right into the advective dispersive transport equation as a source sink. But oftentimes what we do for multiple components, for example, where we've got lots and lots of different kinds of reactions, then what we couple these two processes. And so let's, so coupling of reaction and transport is a really complicated and fraught process, and there's a lot of ways to do it. So let's just think about first of all our full 3D advection dispersion equation with reactions. And I'm going to write it in compact notation. Gradient of the dispersivity, hydrodynamic dispersivity tensor times grad C. So that's my dispersive term minus grad dot V, the velocity field. This V bar means it's a vector field times C plus R. All right, these are our reactions, our sources and sinks, is equal to dC dt. And this R can be any or all the processes, the reactions we've discussed. So there's a variety of ways we include this R in our term. And we've already given one example where we just wrote the R directly into the equation, sort of solve the equation, we get the retardation factor. If these things get really, really complicated, adding them directly into the equation can get more complicated. And so we can couple the two processes. And so what I'm going to do here is draw a cartoon of the geochemical and transport coupling that we can consider. And that is the common modes of coupling these two equations together in the field right now. Okay, so the tightest coupling, and I'm going to illustrate that here at this box, where we include all include everything in one equation, all right? And our retardation equation is an example of that. We put that reaction directly into one equation. and we write all terms in that one equation. We solve that one PDE simultaneously, all right? So the next scheme is called sequential iteration. So I'm gonna draw a hypothetical boundary here. And on one side, we've got solute transport, and this is advection and dispersion, all right? And on the other side, we have geochem, and this is all the reactions, all right? So in the tightest coupling, we're gonna put both of these into one equation and solve them. The other way we can do it is what we call sequential iteration. So in sequential iteration, we take one time step in solute transport. All right, so basically we move solutes via advection and dispersion. All right, and then we do chemistry. So we have a new distribution of solutes in different places. They're exposed to different minerals, and so then we do geochemistry. So we iterate and we solve all those mass balance equations that we talked about above here, all right? And so this is called sequential iteration. We iterate on solute transport, and then we iterate on chemistry. Um, so another way we can do this is non-sequential iteration. So here we do one time step. Here we do one time step here. And these time steps are not equal. So this guy is not equal to this guy. And so you can think about this as two sort of zombie processes, and they're not really interacting, all right? And this is non-sequential iteration. So we just take one time step in fluid flow, and then we take another time step in chemistry. Another step up here, and this is the one that we are going to use. This non-sequential iteration, this one I've never really seen used, but this one gets used a lot. And this is where you solve all time steps. Solve all transport. Then solve all chemistry. And basically what that means is that here they're very loosely coupled. Transport isn't affecting chemistry all that much, and chemistry isn't affecting solute. And then the highest level is this, well, this one we just consider transport only. All right, so this is conservative transport, and this one is chemistry only, and this is what we call batch chemistry. All right, and these are the sort of levels of coupling. I would say the most common levels for the codes that we use are going to be either this one, all right, for simple equations or this one, where we solve one guy and then we catch the chemistry up. And then we solve another step of the transport and then we catch the chemistry up. And these are the tightest coupling between these two processes and the ones that we're mostly going to use. These other ones, the farther we go out this box, the less transport and geochemistry are coupled together. And so the less we care about the reactions essentially and how they affect, how the transport affects them. All right, we're going to stop there for today. In our next lecture, what we're going to do is consider first order decay, write it into one equation, and then we're going to develop an Ogata-Banks solution for first order decay and absorption and play around with it. So hope you enjoyed the lecture. I hope you have a good day. Vote 2020, and we'll talk to you guys later. Bye.